I'm so sorry. I'm so sorry. I was late. Okay. So my streaming stuff wasn't set up, and then my monitor wasn't turning on, so I'm having to stream from my laptop now, which is, oh god. Um, I was not really. That was not my plan. I don't know. I really hope my monitor's not broken. 'Cause that would not. That wouldn't be good. It's just, yeah. Um, no, I'm having to stream from my laptop now, which it's not as ideal. Oh boy, because my laptop, I also use it to chat, but now I can't do that if it's the device I'm streaming on. Oh gosh. I don't know how to change bitrate. I'm sorry. Um, I have no. I'm late, and then no one shows up. Yeah, that's perfect. That's perfect. I just, ugh, so upsetting. Well, uh, what to do? Well, I guess for any VOD viewers, I can still present it anyway, and um, yeah, just still present it anyway, and then, you have something to watch there. Ugh, I'm sorry. All right. Ooh. So yeah, thanks, Granby. All right, let's go ahead and get set. Okay, so I guess for those who don't know, my very first video was about the Kardashev scale. It was a short video, just kind of introducing and going over a lot of the very basic concepts, and especially if you compare it to my more recent videos, it's not that good. So that's why I'm going to be revisiting it. Yes, that's what we're going to be doing. Ugh. In addition, we're also going to be reading the original um paper that Kardashev wrote. Going over that, I think that's gonna be fun. We're gonna do that at the end. But I think first let's do the presentation, just because it'll help give you like grounded in context. Oh, dang it! There we go. How big do we want this? I think that's good. Okay. All right. So, oh my god. Maybe I shouldn't have been doing a presentation early in the morning for me. All right. Ugh. Alright, first off, let's go over the creator of the scale. Nikolai Kardashev. He was a Soviet-Russian astrophysicist who proposed the scale in 63 or 64 at the Burykin Astronomical Conference. The proposed scale is that you can measure the levels of civilizational growth by their energy consumption. What he in his initial proposal, he gave 3 different scales or 3 different levels. Type 1, which is able to oh my god. Type 1 civilizations have energy control over their home planet, which for us is around 2 times 10 to the 17 watts. Type 2 would have energy control over their whole star, around 4 times 10 to 26 watts. And then type 3 has energy control over the entire host galaxy, 4 times 10 to the 37 watts. Ugh. And we're going to be reading a lot of the original detail. Yeah. Ugh. I shouldn't have done this in the middle of the week. Ugh. Regretting my decisions. But it's fine. It's fine. Alright. Now, ever since Kardashev first proposed the idea, a lot of the scale has been expanded on and refined, most notably by American astronomer Carl Sagan. He expanded the scale to provide more intermediary between the three main steps, using this broad equation, which I honestly don't remember what the variables mean, but it places humanity on as a 0.73 type, which isn't even type 1, but we are close. We could get there within the next 100 so years, assuming we survive. Maybe. Alright. And of course, others have expanded upon the definitions and implications of what each level of civilization would mean, like things like resource mastery, as well as a civilization's general level of resilience. Right. Now, what might these civilizations look like? Well, let's see. Type 1 civilizations would have resource mastery and control over the whole planet. But will they live in... Oh, God. The question is, yeah, obviously they have energy control over their whole planet, but do they live harmoniously with nature, or do they attempt to claim mastery over it? It's kind of a question. It's just because I think, especially when it comes to climate crisis. Oh God, this is not going well. I don't remember what point I was trying to make, but it's okay. So, Type 1 civilizations have energy control over their whole planet. So, would that also? I think that would all. Would that? Oh God. My God. Ugh. Ugh. I'm sorry, y'all. This is not going too well. I I'm just T-Rake. Maybe, yeah, cause I'm just kind of messed up cause like I mentioned, my monitor is broken, or seemingly, because it wasn't turning on. So I'm having to use my laptop as a backup streaming device, and it's just kind of stressing me out and just throwing me off. Yeah, you know what? I'm just gonna real quick. I think I don't have a proper be back soon screen, so hold on. All right, I'm just. Ooh. Yeah. Out. All right, I'll be back. Um, turn that off. All right. Hold on. Hold on. I'm back. Oh no, come on. I'm back now. Hi. Sorry about that. I was just. No, it's all good. We're all good. And I suddenly remember what I was trying to. The point I was making here. So, the idea behind the Type 1 civilization is that they managed to achieve complete energy control over their home planet. Basically, all the energy that their planet receives, they are able to harvest and utilize. But the question is, like, would the civilization manage to exist within nature and within the vast ecological system, or would they manage to surpass that and achieve, like, in a sense, mastery of nature? Because humanity, despite what we might think, we're still very much interconnected with the natural ecosystem. But part of the question is that if the definition of a Type 1 is that you have complete energy control over your planet, does that necessitate having complete control over the environment? It's something I don't actually. Yeah, I'm sorry. My brain was kind of clouded, and I needed a break. But I'm back. We're all good, and I really don't know what to do about this stream's bitrate. I don't know what you want. That's an interesting question. It's one I don't actually know the answer to. But I think it's something to think about. I mean, sorry. I got some cookies as well. I mean, I think right now, understanding our place within the environment is a very crucial thing if we want to continue living on this planet. But the question, of course, remains if that's just a temporary arrangement, if we'll eventually surpass that, which I certainly don't know. What kind of cookies? They're like lemonade type cookies. I got gifted some Girl Scout cookies. That's what they are. Anyway, when it comes to the greatest society of a Type 1 civilization, a large part of it assumes a level of planetary unification, globalization, and interconnectedness, because in order to have resource mastery over your planet, resource and energy mastery over your planet, you need to be able to have a global interconnected system. And such a civilization could also be near a post-scarcity situation where the scarcity of basic goods needed for survival is functionally eliminated. But that doesn't mean it could apply to everyone, because just having a lot of resources doesn't mean everyone has equal access to them. Having a lot of resource and energy doesn't mean people often try to go short-term happiness over long-term survival. I mean, a lot of it depends on societal context and material conditions. But what could a Type 2 civilization look like? Well, in order to be able to harvest the power of their host star, they need a large-scale megastructure, namely Dyson Sphere, Dyson Swarm, which I am making a full video on this. It's been delayed, but it's in the works. I hope to get it out soon. And Type 2 civilization would have most likely colonized their solar system because it allows for easy construction of said megastructure, as well as harvesting and storing of the energy. But technically, under the definition, it isn't strictly required. You could have a Type 2 civilization, for example, could live entirely on a Dyson sphere, in the sense of the Dyson sphere is made up of orbital habitats, or the Dyson sphere is used to power one large computer, which they all live in, as in they upload their consciousness onto the computer. I don't know. That's also going to be part of the video I'm making. I'm gonna explore that a bit. Okay. Lastly, what would a Type 3 civilization look like? Well, obviously, as we already know, they would have entry control over the entire galaxy, which would necessitate them being a galaxy spanning civilization. Now, there are a lot of forms that this could take, and they're highly speculative. It could be if they have faster than light travel, which is like basically fantasy just because the laws of physics currently prevent it. And that could be, it could stay as one unified cohesive entity. If the travel is capped at the speed of light or at sublight travel, then that's going to severely hamper the ability to not only become a Type 3 civilization, but to also keep expanding. Or maybe a self-replicating nanite swarm that goes out, builds megastructures, and harvests energy and resources over the galaxy, also known as the Berserker hypothesis to the Dark Force, the Fermi paradox. Alright. And is it possible to go beyond a Type 3 civilization? Depending on like various levels of scaling, they would have control over galactic clusters or the entire observable universe. Kardashev didn't consider such a civilization to even be remotely possible, and you know what? I agree, because for one, expanding beyond your host galaxy into other galaxies necessitates intergalactic travel, which like even with like various forms of faster than light travel, or like even at light speed, like that's a pretty much impossible journey. And like even if you could make it, it makes having a single cohesive civilization impossible because of the vast distances involved. Now, another thing that affects even Type 2 civilizations would be pretty difficult to. Yeah, that's saying Type 2, Type 3 civilization, well, especially Type 3 civilizations and potentially beyond. The big hampering effect is just communication speed, and that's actually part of another video I'm working on. It probably won't come out anytime soon, but it's on the roadmap I posted at the beginning of the year. But for the last part of the presentation, why haven't we found any like of these civilizations, even any evidence of them? This, of course, is a question of the Fermi paradox. We have a model for what these advanced civilizations might look like. So the question is, where are they? We've seen no signs that any level of these civilizations exist, or even remnants showing that they had exist. And it does kind of call the question of what if our model is wrong? What if we're kind of approaching this in the wrong way? What if civilizations might not even reach such a stage? Might not even, like, for example, might not even reach Type 1 because of various factors that might prevent it or are inherent to civilization. But let's go over how we might detect the different types. Detecting a Type 1 civilization would kind of be the most straightforward because they'd be at a similar level to technological level to us. It'd be a bit more advanced, but not totally incomprehensible. There would be some recognizable technologies and signs of technosignatures, like city lights or radio signals. Detecting Type 2, well, that comes down to trying to detect the Dyson spheres. One of the main ways we can go about this is atypical stellar spectra, because the Dyson spheres would impact the light that we receive from the star and would show, for example, metals and chemicals that would not be typical in a star of that size or class. And we've had multiple potential leads on Dyson spheres, but have all either been false alarms or inconclusive, oftentimes just dust. One example here is Tabby Star. Like I said, it was thought to be a Dyson sphere candidate, but turns out it was later confirmed to just be dust in the way. kind of embarrassing. What if they do exist, but in other galaxies or so far away from us that life in them is like to reach us or like us? They haven't even. Yeah, that's. I mean, yeah, that's the with the infinite scale of the universe, or even like the near infinite scale of the observable universe. It might just be that space is too big, that it's too spread out, and like the odds of life are so low that just the civilizations are so rare. And like I said, they we could be early. We could be like early in the galactic stage of development. Who knows? Hmm. And lastly, detecting type 3. Well, if a type 3 civilization existed here in the Milky Way, we should be able to see the signs everywhere, remnants of Dyson spheres. But maybe one doesn't exist or never existed here in our galaxy. Or maybe we're going about looking at it wrong. Our model, like I said, going back to the question of if our model is correct, maybe the general model is correct, but we are going about the wrong way trying to detect them because the civilizations become increasingly more incomprehensible to us, that the way we're looking for them is incorrect. All right. Well, we went through the context presentation. Now it's time for the fun part, paper reading. Isn't that fun? All right, hold up. Let me get it pulled up. Ooh. All right. Um. Hell yeah. Hold on. Give me a minute, cause I'm actually kind of scared that this. I need to find a way to open this that doesn't dox me, because I have it saved to my computer, but I don't want to. I want to make sure it doesn't reveal my name on accident. All right, hold up. Um. All right, hold up. I think this works. Let me just double check. Um. All right. Yeah. Ooh, paper reading time. All right, let's get started. Transmission of information by extraterrestrial civilizations. In S. Kardashev. The P.K. Sternberg Astronomical Institute. Translate from Astronomical. I'm sorry. Astronomiczny Journal, Volume 41, Number 2. Original article submitted December 12, 1963. The protracted duration of signal propagation is a determining factor in the one-way transmission of information through space. Reliable reception, or any reception at all, of signals by unknown subscribers necessarily requires an isotropic emission. The optimal signal spectrum for transmitting the maximum amount of information in the presence of quantum noise in the background of cosmic radio frequency emission has been calculated. It is shown that a civilization located at any distance in the universe and in possession of a power to the order of L. Oh, I feel like I should know what that's. L star. Is that? No, I don't think. It is roughly equivalent to 4 times 10 to the 33 erg seconds or more, which it is capable of transmitting an encoded isotropic radio frequency signal, may be detected by conventional radio astronomical techniques. The expected distinguishing properties of artificial sources of cosmic radio frequency emissions are enumerated. It's speculated that some sources known to us today, notably CTA-21 and CTA-102, may be artificial radio sources. Okay, I think that's what the abstract. I can't believe Stella's real name is Kardashev. Oh no. Ast- astronomy. Yeah, I'm really sorry. Yeah, but no. I think okay, but this is what the abstract is saying. It's basically saying that the yeah, this is the abstract, and I think what it's saying is that the the level of like basically how the level of like energy of civilization we need to transmit information has been found to be this value for around 4.4 times 10 to the 33 erg secs, and that some sources, some radio sources in space may be artificial. So I'm looking through it. It's like this kind of a unique paper format because it's not like super old. It was back in the 1960s, but still, it's definitely different from what I'm normally see today. All right, let's keep reading. Mm, mm, sorry. The principal factors which exert a determining effect on the range of space radio communications are the transparency of the not interstellar medium to radio signals, the level of the equipment noise and space noise, and the power of the transmitters. The greatest possible range for establishing space communication could be said to likely be in the range of 10 to the 9th to 10 to the 11th CPS. The absorption coefficient for the interstellar medium is negligibly small at these frequencies. The equivalent noise temperature may be represented in the form of T to the N equals T to the N plus T to the T plus T to the Q, where T to the N and T to the T are respectively the temperature due to synchrotron radiation and due to the background thermal cosmic radio emission. And T to the Q equals H of F divided by K is the equivalent noise temperature due to quantum fluctuations in the minimal detectable signals. H and K are the Planck constant and the Boltzmann constant. Alright, yeah. Oh my god, my laptop is... fans are going wild. Apparently the paper is too much for them. It's too high energy. No, I think it's because it's streaming, but... Alright. Let's see. The expression for T to the N gives an estimate of the limiting sensitivity, which might be achieved in the case of an ideal noise-free receiver and observations outside the Earth's atmosphere. In Figure 1, we find plots of T to the N as a function of the frequency in accord with up-to-date radio astronomy data. Alright, this is Figure 1. Noise spectrum outside the confines of its atmosphere is... Okay, it's the thick line. And the direction pointing towards the center of the galaxy, in the direction of the galactic pole. Alright, I don't know what this means. I think it's just repeating. Okay, yeah, it's plotting out like the date, the current, the astronomical radio astronomy data at the time. You stream on my laptop? No, I don't usually, but my monitor my monitor went kaput. I don't know what happened. It's like it wasn't turning on with the computer, and so I really hope it's not broken, but we'll just see. The paramount role in the establishing of long-range communications within the confines of our galaxy will evidently be played by thermal and non-thermal radio frequency emission from the galactic disk over a range of plus or minus 50 degrees in longitude on either side of the center of the galaxy. In that case, we have T to the N equals 2 times 10 to the 27 times F of negative 2, 9 plus 10 to the 19th F of negative 2 plus 4, 8 times 10, or is it 4.8? It might be, because I know it might be negative 2.9 and 4.8, and they just use commas instead of periods to denote like decimal places. That's weird. Times 10 to the negative 11th f. Alright. 10. Alright. Could type 1 civilization never go to space? I mean, theoretically, because it's they managed to harvest like, because definition is just being able to have energy control over their home planet. So apparently the amount of noise reaches a minimum for a specific frequency. Yeah, that seems to be what is trying to be communicated here. The someone needs to write an astrobyte over this. Well, that's I think that's what it's being communicated here. There's a range of frequencies, like range of energy frequencies that, oh god. Yeah. Yes, I have not yet taken a radio astronomy class. I hope to. Maybe that'll help me understand what's being communicated here a bit better, but I'm still having fun reading. Okay. In dealing with the problem of possible successes and dealing with setting up communications between the galaxies, we must take into consideration the brightness, temperature of the background at high galactic latitudes, which is due to synchrotron radiation from the halo and the metagalaxy. What is a metagalaxy? It sounds like the metaverse. Oh, it just refers to it's an old term referring to like large scale galactic systems. What is synchrotron? I'm sorry, I'm having to Google a lot of terms. Synchrotron. Electromagnetic radiation when emitted when relativistic charged particles accelerated perpendicular to their velocity. Okay, yeah, it's just a type of radiation. Galaxy, all the pros spawn in. It's normal in Russia. The commas as decimal place markers. That's that's not how we do it in American. All right. In this case, we have t to the n equals 10 to 28 times f of negative 2.9. Oh, no, wait, no, hold on, look here. It uses decimal placement there. So, I don't know, maybe... That's weird. Right. Plus 4.8 times 10 to the negative 11th f. In both cases, the noise temperature will display a deep sloping minimum, which the decimeter and centimeter wavelength ranges, which renders this range more suitable for communication over exceptionally vast distances. Okay, that was all bullet point 1. I think what's being communicated here is that there's a range in which communication over like the vast, like the distances of space is ideal and like most effective, and that range is demonstrated in this graph here. Whatever your finger is closest to when typing. Yeah, I know. I'm just messing around. I'm just not used to it. All right. 2. Let us evaluate the information context of communication channels for the application to this problem. The upper bound of the rate of information transmission at a specified range transmitted power and specified noise distribution is determined by the corresponding Shannon theorem. R equals the integral along the range of f1 to f2 of log base 2 s of f plus n of f divided by n of f times what in respect to d of f, where s of f and n of f are the functions of the spectral power of the spectral power density, of the useful signal, and of the noise, respectively. Alright, useful signal, yeah, S, the noise, and of it. Alright, by solving the appropriate variational problem, you may show the maximum rate of information transmission to be achieved under the condition of S of F equals plus N of F equals N F1 equals N F2. Alright, so it looks like now we're looking at the maximum range, sorry. It mentions it, so that the upper bound of information, of like how much information can be transmitted in a signal at varying times. Alright. Here, F1 and F2 are the bounds of the transmitter transmission band. It is accordingly quite clear that the spectrum of the artificial source must display the shape of the curve in figure 1, but with the sign reversed. S of F equals N of F1 minus N of F, i.e. the spectrum of the artificial radio emission must feature maximum, and in a region of frequencies lower than this, the frequency will fall as A minus B of F to the negative 2.9, whereas in a region of higher frequencies, it will fall as A minus C of F. A, C, and B here are constants depending on the power and bandwidth of the transmitters and on noise distribution. Alright, so what I'm getting so far is just I kind of yapping and like interrupting myself when reading, because like I like to kind of process when reading. Like it seems, yeah, it's the level of like you need higher energy to be able to transmit farther distances, and it's also impacted by noise between like transmission source and destination. Okay. To make a rough estimate of the rate of information transmission, there is of course no need to take the logarithmic term in Shannon's theorem into account. The rate of information transmission, R equals F2 minus F1 equals delta F, then IE will be equal to the system bandwidth. Let P be the transmitter power, and we shall assume the radiation isotropic. There appears to be no point, in our view, in discussing the possibility of establishing outer space communications when high directivity antennas are being used for transmission, since the probability of success in establishing such transmissions is virtually nil. Oh, okay. So she's like proposing a way, like how to go about steady communication because of various power levels and just effectiveness. I really hope this is entertaining to you all. It was literally just me reading the paper and then kind of nerding out about it. Alright. While occasionally eating cookies. Alright. The high direct... Try that again. The high directivity of the radiation can be conveniently used, in all probability, only after a two-way communication exchange has been set up. And if we bear in mind the fact that the distances between two civilizations in question may be comparable to or even more enormous than the dimensions of our galaxy, then this second mode of communication may be brought to fruition much later. In the meantime, the need for isotropic radiation geared to establish contact with new potential listeners will not have abated. Let the transmission be carried out over bandwidth of delta F. Let the maximum expected distance of the transmission be R, with A the effective area presented by the receiving antenna, T of N the noise temperature referred to the input of the receiving antenna. We shall assume the transmission to be reliable when the condition 100 KTN equals PA divided by 4 pi r squared delta F is fulfilled, i.e., when there's a 100-fold excess of signal over noise, then delta F equals PA divided by 400 pi r squared KTN. Consequently, the channel capacity will not be less than delta F bits per second. The radio emission flux per unit frequency interval will not be less than F of F equals 100 KTN divided by A. Very interesting. This is... Alright. I wonder when he's going to propose the idea of the Kardashev scale itself, or if that was like proposed at the conference itself and not in the paper. Let's keep reading. Let's see. The most important parameter to deal with this in this problem is not power P, about which several hypotheses are in order. Calculations show that the total energy quantity of energy expended by all of mankind per second at the present time is about 4 times 10 to the 19th erg, and the annual increase in this energy expenditure is placed at 3 to 4% over the next 60 years on the basis of statistical findings. Now, let this increment represent an annual increase in energy consumption by a factor of 1 plus x. So that in t years, the increase will be 1 plus x to the t power is roughly equivalent to e to the tx times, with x, that's some unfamiliar notation. It might be, I guess it's another part of like reading old papers, you might see some more archaic notation. I think that might be saying x is less than or equal to 1. Alright. Assuming x equals 1%, we'll find that the energy consumption per second will be equal to the output of the sun per second 3,200 years from now, i.e. 4 times 10 to the 33 erg per second. And at 5,800 years, the energy consumption will be equal to the output of 10 to the 11th stars like the sun. Okay, so now he's giving a figure for like the growth rate of energy consumption and like how quickly a civilization would advance, assuming of course constant like increase in energy consumption and growth. The figures arrived at seem to be inordinately high when compared to the present level of development. We see no reasons why the tempo of increase in energy consumption should fall substantially than predicted. Moreover, the availability of a large amount of information forthcoming from other and more highly developed civilizations might contribute to a staggering increase in energy consumption. In line with the estimates arrived at, it will prove convenient to classify technologically developed civilizations into 3 types. Oh, here we go. Alright. 1. Type 1. Technological level close to the level presently attained on Earth, which energy consumption at around 4 times 10 to the 19th erg per second. Type 2. A civilization capable of harnessing the energy radiated by its own star. Example, the stage of successful construction of a Dyson sphere. No way he said the thing. Energy consumption 4 times 10 to the 33 erg per second. I think the figures he's like giving... yeah, there we go. I think double less than might just mean a lot less. Maybe. I'm not too sure. The word... No, hold on. I'm gonna check something. Because the figures... I think the figures with it, like, compared... Yeah, the figures are different when it comes to energy level. I think it's because it's using a different, like, measurement of energy. But here we go. He proposes the 3 civilizational level types. Alright. 4. Estimates of the possibility of detecting a Type 1 civilization, 7, and related experiments in the OZMA, I don't know, projects in the USA have revealed the extremely low probability of such an event. Consider the possibility of detection and reception of information sent by Type 2 and Type 3 civilizations. First of all, we assume here that one of the principal tasks of such communication efforts would be the transmission of information from a more highly developed civilization to a less highly developed one. Starting from the present level of development of radio physics as point of departure, we see in principle that it's possible to build antennas within the next 2 decades with an effective area of 10 to the 5th meters squared and with receiving apparatus featuring a noise temperature T to the N is roughly equivalent to 1 Kelvin. If a transmitter is designed for the system to receive and record information, equation 3 will show that the radio emission flux at the receiving point will not be less than 1.4 times 10 to the negative 27 W flux. I don't know what big W divided by M squared. CPS, an amount which is well within the recording. CPS, an amount which is well within recording capabilities of presently existing radio telescopes. What browser is that? Okay, I initially had it opened in my browser, but it would have doxed me. So instead, I just have it opened in Adobe PDF Reader, which I only installed because it was the first PDF reader. But I don't use it because it has AI bloat, and I don't use it. I just use it to. I normally use the browser to read PDFs, but in this case, I'm using this. Alright. Of course, for a simpler equipment, we'll require to detect the signal, since, in contrast to the reception of information, here we may utilize the averaging techniques common in radio astronomy, and radiometric gain square root of delta F of tau. I think that's tau. I think that, because I know tau looks like T, but it's like not. It's like very slightly different from T. Yeah, no, that's tau. Where tau is the build-up time. May enhance the sensitivity by 3 to 4 orders of magnitude over a fairly wide signal band. We now cite some estimates of the quantity of information attainable in line with Formula 2. For Type 2 civilization, we have to take into account the frequency variation of T to the N as in accord with Formula 1. T to the N equals 1 Kelvin is assumed for Type 2 civilizations. Table lists estimate for 3 distances corresponding to transmission of information within the confines of the galaxy, within the confines of a local system of galaxies, and within the confines of a portion of the meta-galaxy accessible to observation. The estimates arrived at show that there should exist even one Type 2 civilization within the confines of the local system of galaxies. There will be a realistic probability of securing an enormous quantity. Oh wait, no, hold on. The estimates show that should there exist even one Type 2 civilization within the confines of the local system of galaxies, there will be a realistic probability of securing an enormous quantity of information. The same holds for the existence of even one single Type 3 civilization in the portion of the universe accessible to observation. Alright. For the purposes of comparison, let us estimate the time required to transmit 10 to the 8 printed and manuscript form publications now available on the Earth for the channel of 10 to the 9 CPS bandwidth. Assuming that each written work contains an average of about 10 to the 6 bits of information, find that the total quantity of 10 to the 14 bits of transmission may be transmitted in 10 to the 5 seconds, i.e. in a single day. However, it is quite evident that there is no need to transmit all of the 100 million publications in order to broadcast the principal data on the status of science, technology, and culture on Earth. Such information would contain a colossal amount of redundancy. Apparently, all the basic information that could be compressed in 10 to the 5 books of 10 to the 6 bits each would come to 10 to the 11th bits and would take only 100 seconds to be transmitted via the same communications channel. Finally, it is entirely reasonable to assume that Type 2 and Type 3 civilizations would be possession of information of many orders of magnitude in excess of what we have available at the present time. For that reason, they would have to be broadcasting practically continually, and this would also be the case for increasing the possibility of reception by Type 1 civilizations. Moreover, in order to improve the reliability of the information received, in order to afford some new opportunity to make connections with new subscribers, there had to be periodic repetition of the program's broadcast. Okay, so what I think what's being established there is that if even one Type 2 or Type 3 civilization existed within a range that we could detect them, we would definitely we should be receiving a lot of information from them, the being transmitted out, assuming they were, of course, transmitting it out. Which, I mean, we do. We transmit a lot of information out. But, alright. Number of bits per second, roughly delta F. Transmission power. Alright. R equals 100,000 light years. 3 times 10 to the 9. R equals 10 million light years. 3 times 10 to the 5. Okay, in both cases, 10 billion light years is too much. Transmission of large quantity of information, impossible. 3 times 10 to the 10th power. Yeah, so even with a high transmission power, it's too much. Oh, no, that's just for Type 2. Type 3, is it? I don't know. Subscribers. Yeah, I'm not sure what was, like, meant by that. Maybe, like, subscribers in the sense of lesser civilizations listening in on more advanced transmissions. I'm not sure. Let's keep going. Note again that, in all likelihood, a Type 1 civilization would be capable of sending a turn signal only after its energy consumption had increased measurably. Consequently, the communications would be a long one-way affair at the start, and the problem of how long it takes signals to propagate would be a second one. As it is evident from the above estimates of transmission of transmitter power for Type 2 and Type 3 civilizations, the figures are very close to the power of synchrotron radiation from the nebulous form and supernova explosions or from radio galaxies. Calculations of the optimum transmitter bandwidth show that the transmission spectrum may also closely resemble the spectra of discrete radio sources. Several criteria could be singled out which would be useful in discriminating artificial radio sources from the vast number of radio stars accessible to observation. The artificial sources would evidently, 1, have to be very small angular dimensions, at least in the case of Type 2 civilizations. The angular dimensions would have to be on the order of the angular dimension of stars, i.e. less than 0.001 seconds. That's a really... Because, minutes are, fractions of degrees, and seconds are fractions of minutes. Yeah, as in people listening in, but it's funny to think of YouTube subscriptions, I guess. Alright. The now known natural radio sources must have appreciably larger angular dimensions, larger than 0.01 seconds. In fact, according to Theory 8, larger than, in fact, according to Theory 8. I think those are citations. 2, they would have to possess circular polarization so that the effects of the Faraday rotation in the plane of polarization in the interstellar medium would not distort the information received. 3, they would have to exhibit variability in time without leading to statistical fluctuations. This is obviously a criterion of outstanding importance, but it's possible that regularity and time variation of the signal might might be revealed only in the course of observations using special equipment of wide bandwidth, 10 to 9 CPS, and a sufficient sensitivity to operate with within very short constants. 4. Finally, it is to be anticipated that certain details would be present in the spectrum of the source suspected of artificiality, which have been designated for the express purpose of emphasizing its artificial origin. In particular, we might anticipate such a feature in the environs of the 21 centimeter wavelength line. Information transmission at that frequency within the confines of the galaxy would be inadvisable, since the signal would be strongly absorbed by the neutral hydrogen. It would be reasonable, for that reason, to eliminate the band of 1 to 2 MC. Is that like megacentimeter? I'm not sure what that real notation means. Say rectangular shape in the continuous spectrum of the artificial source, to lay special emphasis on the unusual nature of the radiation. Considerations involving the anticipated shape of the complete spectrum of these artificial sources also deserves close attention. These arguments are cited above when the estimate was made of the quantity of information which could be transmitted. The most characteristic feature of the spectrum is the linear dependence of the flux on frequency in the high frequency region of the spectrum. I guess see figure 2. Oh, here's figure 2. Alright, figure 2. The solid line is anticipated emission spectrum of radio transmitters of extraterrestrial civilizations. The dotted line is the spectrum of radio sources CTA21 and CTA102, suspected of being of artificial sources, and the spectrum of natural radio source Virgo A. Alright. Trying to look at what exactly is being conveyed in the figure. Oh, I think it's it has the same general arc as even if it's not in the same region, it has the same general arc as what's anticipated as radio transmissions from extraterrestrials. Let me actually look. I wonder if data has been looked at since on these two. CTA. Oh, if I can find anything. See. I'm not sure. I mean, it feels like kind of an obscure thing. Maybe I do some more digging. It is consequently of the utmost importance to carry out a program of studying discrete radio sources in the immediate future, with due attention paid to the spectral features mentioned here. Note that even at the present time, we have knowledge of about 20 to 30 or so radio sources, with the upper limit of the angular dimensions in the range of 1 to 10 seconds of arc. Some of these sources have been identified with peculiar optical objects of the nature which is still obscure. Most of them have not yet been successfully identified with optical objects. For example, two sources of radio frequency emission from outer space, CTA21 and CTA102, were recently discovered at California Technological Institute. Display angular dimensions not less than 20 seconds, and have not been identified with a single one of the optical objects in the Palomar sky charts. And to be more intriguing, these sources exhibit a spectrum highly similar to the anticipated artificial spectrum. Figure 2 presents the observational data in 12 on these two sources, along with the theoretically predicted spectrum. For purposes of comparison, the spectrum of a typical natural radio source, Virgo A, is added. The scale is compressed by a factor of 10 on the ordinate axis in the case of Virgo A. I see. I was just talking about the figure we just looked at here. Yeah, I mentioned like it's the fact that they weren't able to find a real match, and that the arc looks similar to what is anticipated from extraterrestrial transmissions. The most promising region for search for artificial radio signals is apparently in the direction towards the center of the galaxy, since the density of the cell population is greatest there along the line of sight. It would also be appropriate to investigate the closest galaxies. In the first instance, a large nebula in the Andromeda constellation and the large Magellanic Clouds, as well as the closest radio galaxies NGC 4486 and NGC 5182. In conclusion, we would like to note that the estimates arrived here are unquestionably of no more than a tentative nature. But all of them bear witness to the fact that if terrestrial civilization is not a unique phenomenon in the entire universe, and the possibility of establishing contact with other civilizations by means of present-day radio physics capabilities is entirely realistic. At the same time, it is very difficult to accept the notion that out of all the 10 to 11 stars present in our galaxy, only near the sun has a civilization developed. It's still more difficult to extend this inference to 10 to 10 galaxies existing within the portion of the universe accessible to observation, to the observable universe. In any case, the deciding word on this question is left to experimental verification. In particular, you may anticipate that space rockets will clear up the question of whether or not life exists on other planets in the solar system in the years to come. Discovery of even the very simplest organisms on Mars, for instance, will greatly increase the probability that many Type 2 civilizations exist in the galaxy. Radio astronomical searches could of course play a decisive role in resolving this problem. Alright? Congrats, we just read a paper! and then it's just some final citations. I think that was fun, was it not? I think that was fun. Alright, well, that's all I had planned for this stream. I guess if y'all have any questions about about what we just read or about the Kardashev scale, I can answer them real quick. But other than that, I'm going to start wrapping up. Good nerd talk? Yeah. Thanks. Alright. Well, I think this is what I'm gonna cut off now. When was this? Like, when was the paper published? It was discussed at the conference, the Budokan conference in 1964, but the original article was submitted in December 1963. See, like I said, it was like 1960. That was like, 60 years. Well, it's, I think 62 years at this point. Hold on. 2026 minus 1964. 62 years. Well, I'm going to start wrapping up. I'm going to go ahead and other than this, what achievements in Kardashev have? I'm honestly not sure. Let's see. I know he did radio astronomy. Alright, let's see. Yeah, Korea. Yeah, of course, his main thing was the paper we just read, transmission of information by extraterrestrial civilizations, which proposed this Kardashev scale. Oh, he may have he may have actually predicted the existence of pulsars in the paper. All right. He also proposed a very long baseline infrarometry, which replaced conventional radio transmission lines with magnetic tape recordings. It was demonstrated in 1967. Okay. And like he was looks like he was also involved with the International Astronomical Union as well as the USSR Academy of Sciences. Interesting. Very interesting man. Right. Right. I'm gonna go ahead and end stream now. I need to have lunch. Because lunch is not just cookies. Alright. Well, I'll see you all next stream, which is I don't know. I don't know when next stream is gonna be. It's gonna be sometime. Anyways, short streams, 70 minutes. What did you lose track of time listening to me read a paper? You're welcome. I stole 70 minutes of your life. You're never getting it back. That's all. Goodbye.